This is the Empower Podcast, released May 19th, 2019, episode 443, an interview with JP Norair. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
And I'm JP Norair of Haystack Technologies.
Hey JP, how you doing?
Not bad.
Thanks for joining us here today. I know you actually from the consulting forum. You joined that, and you've been a very valuable contributor there. But the thing that I was really interested in is that we had a conversation going on there roughly that was about it was something about LoRaWAN effectively, and you had started to kind of give me some education about stuff that I didn't quite understand, of like different networks around LoRa and LoRaWAN and other things that are out there. And maybe that's a good way to start, and then we can kind of go back to where all that came from.
Sure. This is a topic that can be extremely expansive or extremely summarized. I'll try to go somewhere in the middle ground and of course ask questions in between if you want to go deeper. But so LoRa is a product from Semtech, and LoRa, the origins are from the mid 2000s, from a couple of French engineers who had a little company, and Semtech ended up buying their technology and productizing it into LoRa. It's a unique modulation among other things of its class. It's chirp spread spectrum. It has good attributes of it, and it's been an improvement over low power radios in the past for a lot of very technical reasons. But it's been an improvement over what had been before in terms of propagation, quality of service. So that means the sort of likelihood of receiving a correct message, performance and multipath. But LoRa is it's a phi layer is what we call it in the industry.
Right. I kind of think about it like the actual low level, like what's actually happening to that 900 megahertz in order to make it into a data packet. Is that a good way to say it?
Well, it's kind of the other way around. It's kind of if you're transmitting, it's how you take some bits and turn them into waves, and from receiving, it's how you take some waves and turn them into bits. But so it's quite novel in that respect, and it's not the first chirp spread spectrum technology ever done. But it's probably one of the first ones that's been put into a cheap little low power, low cost device. So that's what makes it unique from a technology perspective. LoRaWAN is a protocol that utilizes LoRa, and LoRaWAN, the origins of it comes from IBM originally. It was really just, I think, sort of an afterthought research project from a Zurich branch of IBM, and it's grown into more. Semtech started to adopt it. That's the company that sort of brought LoRaWAN to market to begin with, and they formed an alliance around it. And they have partners like the Things Network and maybe a few others. So
it's pretty expansive. I think the number, like Intel's in there. There's a bunch of people in there. So.
Comcast is trying to get in there too.
Yeah.
Well, they just had a press release, I think maybe yesterday, about how they're not going to go after becoming effectively a carrier. That they're
because they were talking about putting it in every cable box at one point. Right?
Yeah, it seems as though they're going more after campus installations now. So their strategy is shifting, which it is totally sensible. I think it's absolutely fine. I don't think that's going to slow down LoRa or LoRaWAN.
Yeah.
But it does sort of tell you about the situation, the market demand of these technologies is that a lot of these users are willing to install their own infrastructure, especially when it's low cost. So especially when it's easy to install. So, the value of paying $3 a month or maybe even $10 a year per device, or $1 a month. I don't know. Everybody has different prices, but I know Sigfox Sigfox was a competitor of LoRaWAN, really, not so much LoRa. They are also they're a French company. I don't know if they're quite as strong as they used to be. They have a very different technology, and they've had some uptake in France, mostly due to the French government really going big on Sigfox. Yeah. But they've installed in a few other metros and so forth, and they've had some vertical success in security, like home security, basically. But they raised too much money, and it just doesn't seem. Yeah, they raised hundreds of millions of dollars, and so it doesn't seem like selling $1 a month subscriptions per device is going to cover what was put into it.
I don't know. You make it up in volume.
Well, I mean, it takes one heck of a lot of volume.
Yeah. Well, and that one too is Sigfox. It always reminded me more of like they wanted to install what it was effectively like cell towers, but for low power devices. And then you sell the service to the users.
Yeah, I mean, but that's sort of LoRaWAN as well. So LoRaWAN is not. Yeah. They're not as vertically integrated. I mean, it's a technology. It's an alliance. It's an industry alliance backed by Semtech and some others, but some more heterogeneous mix of customers and companies. And they have service providers. They have kind of networking companies out there. I think, what's that company? Senate, I think, is one, and they set up a lot of LoRaWAN networks. They're just sort of a LoRaWAN network setup company.
A specialist, yeah.
Yeah, that's sort of what they do, and then Things Network is Things Network would be actually kind of a direct competitor of Sigfox.
Right.
Yeah. So that would be a direct competitor. But anyway, so getting back to that, the beginning, if you're building a device and you have certain things you need to do, and you need some kind of low power, long range wireless networking, and LoRaWAN sort of meets maybe 50% of your requirements, or maybe it meets almost all of them, or maybe it meets almost none. But nonetheless, you need low power, sort of long range machine to machine networking. You can still use LoRa. I mean, you can still use the LoRa hardware, and there are a number of other networking stacks that you can install into your firmware and into your software that are not LoRaWAN. So that's kind of the main difference between some of these like vertical solution providers, like the Things Network or Sigfox, where you're locked into a technology stack, and your business arrangement is with them. It's with the carrier, and you get certified hardware, or maybe you can make your own and then certify it, and you certify it against the Things Network, or you certify it against Sigfox, versus you have a lot of freedom if you're just using LoRa. You have an enormous amount of freedom. You just need to make sure it works. And if you're selling your product into like campus deployments, so campus deployment just means that someone's going to buy your hardware, someone's going to buy your infrastructure, and they're going to set it up and they're going to manage it. And roaming isn't an issue, because it's just you care about it.
Right. You leave the campus, you're no longer covered. Right.
Right. And so there's also and you can extend it from there. I mean, the reality is that both of these things can coexist. Like if I have some technology and I really need it for my campus deployment, like for example, LoRaWAN, you cannot move that much data. The frequency of moving data is quite limited. The maximum you can do is about once per 2 minutes. So I can move one piece of data upstream every 2 minutes. And downstream is not that practical either. Moving data downstream, it's kind of, this is a technology that was really designed, LoRaWAN, with kind of meter reading in mind. I think meter reading was maybe the major use case when they went in and designed it, and that's understandable. It's a big use case. It's got not a huge number of customers, so really good if you're an enterprise and you want to go deploy some technology. It's nice not having to have a lot of different customers. Like retail would be the ultimate opposite of that. When you've got millions of independent customers, like the Bluetooth tracker market would be like the absolute opposite of this. And so it's nice if you don't. The fewer customers you have, I think it's a lot easier to have a market strategy. What they want in version 2, you ask them. Right?
Yeah, right, exactly.
And then they'll tell you.
It's not intuiting and trying it
failing
and reverting.
There's no focus groups. There's no, there's no rooms of 50 people with a half-silvered mirror. And
that's right.
Silicon Valley.
Seen in Silicon Valley. Yep.
Yeah. You don't have any of that. So that's real nice. And especially for industries that are pretty young, the ones that don't have a lot of history and capital and behind them. Yeah.
Well, let's talk about how this relates then to what you designed for Haystack and more on contract. So what did you do as a result of this?
Yeah. So Haystack is a company. It's been around for a little while. On paper since about 2010, but in reality since about 2013. So Haystack was a company that was born out of work I had done for a different company. I was an employee of a company called Savvy, SIVI Technology. And Savvy was eventually bought by Lockheed Martin, the big defense conglomerate. Savvy made wireless tags, active tags, not passive RFID tags, but they made basically wireless sensor tags that go on shipping containers and go on shipping pallets. And the military used these quite extensively between about 1998 maybe and probably even up still today. But these were used for their in-transit visibility network, and eventually,
so like asset tracking, but on a broader scale.
Asset tracking on a global scale. So, like in a typical deployment, they'd have shipping containers full of stuff. They dump them somewhere in the desert or whatever, especially during the sort of Iraq and Afghanistan war era, where they just go and dump a bunch of containers full of stuff somewhere, and the supply people in the military would have to find the stuff. And so this helped them a lot. It's
like finding a cache in a video game.
Well, yeah, pretty much. You may have gone past or gone inside military surplus stores in your lifetime, and you've seen them, and they're still around.
Yeah.
But the old way that the military used to deal with supply chain challenges is to have 10 times as much stuff as you need.
Right.
No, that's actually the number, 10 times. So through in-transit visibility, I think they got it down to about 3 times as much stuff. So that's 3 times, only 3 times.
Only 3.
But that's a big improvement. So through technology, they were able to improve their supply chain and make it more efficient. So that's good. That's good for everyone. But so I guess the reason why I'm bringing this up is that that was a cash cow for Savvy, because they were a sole supplier of this technology that they built. And eventually if you're a sole supplier and you have a DoD customer, what they're going to do is require you to standardize it and license it to your competitors in order so that they can have a multi-vendor
standardize it
contract.
among other people, right?
Yeah, exactly.
Yeah.
So I was involved in that. I got hired to that company to support licensees of this technology, and it was a strange relationship. Like the rest of the company did not like our group. The engineers did not like us. So we were not very popular.
Yeah.
But
why weren't you popular though? Just because you had to
we were basically, we had to exist because the military said you guys need to license your tech. But
you were also butchering the cash cow. Is that kind of the problem?
Yeah, exactly. We were kind of, and it was not because you hire me to do a job, I'm going to do my job. But
sure.
But it was cool because it exposed me a lot to standardization, technology standardization, and wireless technology. At a relatively young age, so this was my late 20s when I was doing this, and we did get the technology they had standardized. So it is an ISO standard, or it's actually ISO. It's not ISO, but so there's a standard called ISO 18000-7, which was the first version of that technology. So and that's the one the military uses. And after we finished that. Yeah,
I was gonna say I just figured out the product name. Okay,
yeah,
we'll
right.
get there. Yeah.
So after we finished that, we finished doing that. I think that was around 2010. We got all wrapped up, and all of the other suppliers and vendors were happy. And we said, okay, well, what's next? So let's take all the things we've learned over the last 12 years, all the new technologies, and make a version 2 of this technology, and try to sell it to commercial and industrial and so forth. And so anything since then, when people now talk about or use -7, which is the product name of this wireless technology, it's this version 2. It's actually not. It has some roots in the defense technology one. But it's not exactly the same technology. It's a modernized version of that. And so then the benefit is that we had all of this marketing. We had this huge, calling it marketing is maybe not exactly what you'd think, but
brand equity behind it.
Yeah, we had this huge group of people who had years and years of experience with this sort of product, and we were all in a room, and we were all trying to, build products to sell to the military. And so there was just an enormous amount of what works, what doesn't work, just knowledge about how to deploy, how to deploy and how to design these sort of mobile wireless data systems. And so because we had all of that, it enabled us to build a spec very easily. We didn't have to go out and figure out.
Didn't take like 10 years like Bluetooth did or whatever.
Well, maybe it does, but Bluetooth also has a lot of people in a room, and they're become very sophisticated. They become very efficient. It didn't used to be that way, but the -7 is way smaller and it's way more grassroots, and it's but the -7 Alliance remains. It's still out there. It's mostly a European presence at this point. The technology itself is used, I think mainly in indoor kind of mapping and indoor location, also in parking lots, other really unsexy things like this, but stuff that needs to get done. And it's at a campus level. It's not, you could call it a WAN since the range can get quite long, but it's not like a cellular system. It's not generally deployed in a roaming way. It's not attempting to be that. It's attempting to be a campus, almost like a LP LAN, if you want to call it that. So,
okay.
So yeah. So So it has LAN-like features as bidirectional communication, and kind of bursty asynchronous access. So it's very different in how it behaves as a networking technology than LoRaWAN. And so it makes a good partner with LoRaWAN is the bottom line. If you have a LoRaWAN network and you want to add some LAN features, Dash 7 is a good option. It's not something that is so mature that you can just go and buy parts for it at this point. But usually the kind of people who are going and contacting me or contacting various people in the Dash 7 community about Dash 7 are people who have tried LoRaWAN and it just hasn't worked for their application from one reason or another. And for the last 7 years or so, we've been adding features as needed, adding technologies as people demand them. So we need to have firmware over the air. Okay, well we'll put that in there. And lately, over the last 3 years, really, it's been all about range. So it's just been how do I get more range? How do I get more quality of service? Semtech and the LoRaWAN Alliance have done a fantastic marketing job. And so we're using a lot the LoRa PHY right now. So we're using the LoRa hardware, not necessarily the LoRaWAN stack. And
can you give us an idea of what the relative distances are, like for just maybe a LoRa chip or transmitter by itself versus when there's maybe quality of service on top of it, or when it's using something else?
So quality of service just means it's kind of more of a high level term. It's not really a technical term, and it's used heavily in the cellular industry. And it just sort of means like, okay, I have packets and I'm transmitting them and you're receiving them correctly. And you're receiving them correctly most of the time and in most conditions. So that's good QoS. That's good quality of service. And if you're not receiving packets, if you're dropping packets, then that's bad quality of service. So you want high quality of service. And there are a lot of ways to get there. The dominant ways of improving quality of service are having methods for retransmission or efficient retransmission, and also error correction, forward error correction. Yep. So you can use this is not there's nothing mysterious or secret about this. Every cellular system is probably hundreds of thousands of man hours are spent by the big players in the cellular industry to improve quality of service through better error correction technology or through countless other ways, improving the antennas and the cellular industry is so mature. They're chasing tenths of decibels. They're really kind of at the 99%, and they're trying to get to 100%. Right. LPWAN is not there. It is not that mature. You can implement like something that Haystack did recently. We have a sort of a history of taking technology from deep space telemetry. So that's technology used for error correction to ground to space probes. And a lot of this stuff is just available. You can just go and download it. Not usually code. It's usually some form of math documentation.
Yeah, algorithms and similar kind of stuff.
Yeah. So I'm not I'm good at math, but I'm not one of these people who's building these error correction schemes. That blows my mind. How they come up with this stuff. But
Can you explain what that is real quick for people that don't know what that is? Yeah. I remember I saw Mike Osman talking about it at like a SDR presentation, and I didn't understand it prior to that, but it's a pretty crazy technology.
It's not a new technology. It's stuff that's been around for a long time. It all goes back, I think, to the 30s or 40s, 1930s or 40s. I guess I got to say now.
Right.
There's a guy, Claude Shannon.
Theory.
Yeah, information theory. So he started it all, and he came up with this thing called the Shannon limit, which is basically what is the best an error correction scheme can be. Theoretical maximum that that you can get of gain, of improvement you can get from error correction. And it's a curve because I can send a lot of redundant information, and so that way it's padding the length of my packet. It's padding the length of it, and I can get like really impressive gain. However, it's not really genuine gain, because if I just slow down the baud rate, I can also get gain. And that's just because, like, if I just slow down the baud rate of a transmission, like, so if I take something that's at 100 kbits and I bring it down to 10 kbits, every bit has 10 times the length of it that you previously had, 10 times the duration. So it's 10 times the energy, if you think about it that way. And if I have 10 times the energy per bit, then I'm going to be 10 times as resilient against noise. So, just by increasing or decreasing the data rate, increasing the length of the bits, I can improve, the chance of sending a correct message. I can decrease my chance of packet loss, but that takes more energy to transmit because it's longer. So, I'm trying to find these trade-offs. I'm trying to build new technologies, and I'm using I loosely. And I assume that I'm just some guy, some communications engineer, right?
Right.
I'm some communications engineer trying to improve the power efficiency and trying to improve the quality of service of my connection, and I can drop the data rate. So that's kind of what Sigfox and LoRaWAN have done. And LoRaWAN's very good at just bringing the data rate down because of the way the modulation works. So the modulation of LoRa, it's very easy for the receiver to track the transmission, and so that means not to lose synchronization with the transmission. It's very, very good for that, and so it enables low data rates to be used, lower data rates than were really feasible with more basic modulation schemes and cheap radios. So if I have like a basic modulation scheme and I want to run it at a really low data rate, I need a pretty sophisticated receiver to track it over such a long period of time. And but LoRa works that way. I mean, with LoRa, I can bring it down, I think, to like 18 BPS if I want, or something.
Yeah, I remember seeing some really low ones. Yeah.
Yeah. So that's kind of the way that LoRaWAN deals with trying to improve, to decrease packet loss. And it's just to bring down the data rate, and Sigfox to a large degree as well. Another way to do it is to add error correction. And error correction, I mean, there is a little bit of built-in error correction in the LoRa hardware, although it doesn't really work. That's
interesting.
I don't know. Actually, so there's a guy, his name is Matt Knight, and he was tasked at some point a few years ago to try to reverse engineer the LoRa PHY specification, and he did. And I mean, we all had our suspicions about it, and then he kind of erased all those suspicions. So credit to Matt Knight. If you're really interested in this stuff, go hit Google, search for I think it's called Matt Knight Reversing LoRa. I think that's it. He has a bunch of presentations, and
hear him on the Amp Hour. I interviewed him at Tour Camp. Short 23-minute interview.
Super. So. Yeah, check that out too. So so the reality is that the integrated error correction in LoRa doesn't really work. It's kind of parasitic, actually. So don't use it.
Okay.
Yeah, don't use it. And so if you want to put error correction on LoRa, you got to do it yourself. If you want to put good error correction on LoRa, you have to do it yourself. And so that's something that I've spent a lot of time in, is doing very good firmware error correction. And that is to add data to the message. So adding bits to the message so that I can reconstruct erroneous bits. And it's very complicated, but like the idea is kind of, I mean, it's like human intelligence is pretty good at error correcting. I mean, we do it all the time and we don't think about it.
Pattern matching and then like estimation.
Pattern matching. Right? And really in this case, so in data error correction, I think the analogy is about, having a vector in a multidimensional space, and it sounds like it's going to go off into some horrible story, but it's pretty. You can think about it in a 3D space, and that's very visualizable. And if this vector gets sort of corrupted a little bit, if I can add points on the vector, if it's not just 2 points, if I can add some points, then I can still kind of figure out which direction it's heading in. If it's not 2 points, if it's more than 2 points. So, if one of those points gets skewed off a little bit, I can still kind of extrapolate if I'm, heading north or south, or 1 or 0. And that's the fundamental concept of error correction. And there's so many different ways to do it. There's so many different mathematical kind of back ends to it. And I don't want to get into that too much.
Well, the one that I had heard is like, and I think this is from the Mike's presentation I saw, was like, okay, you're trying to transmit a 1. You can transmit 1, or you can transmit 1 1, or you can transmit 1 1 0 1, or you can transmit 1 1 0 1 0 1, right? And like the longer that number is, and it's a unique number, and you have that, and then maybe the inverse of it is the other thing, you could start to basically, as you approximate that chunk of a number, it looks more, it's easier and easier to suss out whether that long number you've created and this pattern you've created is supposed to be a 1. Is that a good explanation?
Well, that's sort of one. Yeah, that's the Claude Shannon explanation, more or less. And one implementation, one of the earlier implementations of error correction code is something called a convolutional code, and that's just I encode my data in a certain way based on a generator, which is like a bit pattern. And I can take a moving window across my signal and look at the ones and the zeros and in my message that I'm receiving. And I can map them onto a system of states. And, if I don't have too many errors, I can fix a certain amount of errors because they will, like my signal will sort of coalesce around states, one state or 0 state, effectively. So that's an early form of error correction. So there's another standard. You're going to get alphabet soup if you go into the wireless standards, because like there's 802.11. Everyone knows that. There's so many more.
A lot of 802s.
802.15.4, right? 4, so 802.15.4, and then you got 802.15.4 like A through X or whatever. So in one of those, I think it's F or G, maybe. They specify a convolutional code for error correction. And the convolutional code, this was something that was implemented on a TI chip many years ago, and I think they just brought it into the standard. But since then, it's been put on a bunch of other chips. I know it's on some ST transceivers and probably others as well. So that convolutional code is pretty simple. It works reasonably well. I mean, you will get some gain out of it. You can get maybe like 3 dB of gain with a fairly naive convolutional code. And so that means that like I'm improving my sensitivity by 2 times because I've got 3 dB.
Yeah.
That's pretty good. I can make it even better if I do it in a non-binary way. And so if instead of my inputs being 0 and 1, I can make my inputs like, 1 or 0 to 255 or 0 to 64. I mean, often it's just 0 to 16. That seems like it's enough for a lot of these. They call it soft decision instead of hard decision, meaning bits 1 and 0. So in these soft decision, I get more gain. I get another 2 or 3 dB just from having it soft decision. I get better coalescing around states in my decoder. So that's always good. It's something that it's hard to do in software. It's hard to have a soft decision decoder written in software using a cheap transceiver because they don't usually give you this information. They don't usually tell you, all right, I've demodulated this part of the signal and I'm going to tell you 15 out of 16. Usually it's just 1 or 0. They clip it for you. So if you're trying to build firmware that does error correction of a low-cost transceiver and you want to get that extra 2 to 3 dB of soft decision decoding, you have to be kind of clever usually. You have to do things that usually you're not going to find in any example code. Or nobody's LoRaWAN library is going to be like flogging the chip is real hard to get that soft decision information. But if you want to really push it, then you can. It's there.
So this is the kind of stuff that you've developed. Then you've developed like an alternative to the basic stacks that are out there. You're saying, and that's like something that you license out as a design.
Yeah, I mean that's something that we do license out, and often it's just something that sweetens the deal. In the consulting, it's tricky to license technology directly. It's tricky to be ARM. It's tricky to be.
It is tricky to be ARM unless you have like SoftBank money. That's sweet SoftBank money, and then you can do a lot of things.
Yeah, or just a huge backlog of success. Right? People really have to trust you to just do pure licensing. And usually your customers are going to have to be pretty big, and they're going to have to develop their own stuff. So a lot of times the technology, the proprietary stuff that we've done is just, it sweetens the deal, right? It's almost for marketing purposes. It's like if someone's going around trying to find a solution to their LoRa problem, why don't we look at the guys who implemented like LDPC error correction over LoRa and get 14 dB gain over, LoRaWAN. Like that sounds incredible.
Right.
Let's talk to these guys.
Yeah,
right?
We should probably talk to them instead of the people who just follow the regular manual, right?
Yeah, right. If you're trying to get the best range, go after the technology that at least claims. Give it a shot, right? Nobody's ever going to just believe you. But if you send them a dev kit, or in our case, like the first thing we usually do is there's an ST dev kit, and we'll say just get the ST dev kit, install this binary on the ST dev kit, and we have a very simple range test, and go off and test it yourself. And if you don't get better range than LoRaWAN, like I don't know what you're doing wrong.
But what are the relative ranges though too? So like if you send someone, they have this dev kit, it gets what, like 500 meters, 1,000 meters.
It depends a lot on environment.
Sure. But so just give me any numbers.
Yeah, sure. So in the 900 megahertz range, if you do like a test that's like a stupid test. So our device is running at 1K, our reference 1K bit per second, which is it sounds really low. It is low, but in the LoRaWAN world, that's sort of in the middle.
Yeah.
So we do 1K, we get better performance than any observable LoRaWAN data rate. So LoRaWAN at 125 bits per second is worse than us at 1K. So if we put it on a high location and you go driving, basically it's until you hit the horizon. And if you put it on a mountain, that's going to be 36 miles or whatever. Yeah. If you put it on the roof of a house, it's going to be less. Maybe like 2 miles, 3 miles. Oh. But I should also say that it depends a lot on the power transmit.
Sure.
But we're using like the LoRa chip. We're not putting any amplifier on it. So you can amplify it. You could get more. I think we would still beat LoRa even with an amp if they had an amp, or LoRaWAN if they had an amp.
Okay, so this is like software making the hardware perform better.
Yeah,
it's
just
great.
It's just pulling bits out of where bits didn't used to be, I guess.
Yeah, just like information, man. It's crazy.
Yeah, just finding information. It's like, it was shocking. The first time I tested it, I actually couldn't believe how well it worked. A lot of times with these low cost radios, one of the issues is that the tracking is just a problem. So if I just don't have that strong of a signal, it's just going to lose timing. It's going to lose synchronization. It's going to lose bit synchronization. But LoRa seems to not have that problem. And this really enables some strong error correction, much stronger than on like a standard like PSK channel, phase shift keying, or an FSK channel.
Yep.
So that's really cool. I mean, like, I would love. I think there's a huge opportunity for LoRa to have future versions with much better error correction. I mean, they could improve their throughput enormously, because the PHY can take it. The PHY can it won't lose tracking. It's really the encoding itself becomes the the weakest link, I guess.
Yeah. That's great. Well, you mentioned you work with a lot of startups on this kind of stuff as well. So like, how does that end up manifesting with, is it that's who's pushing for the range in this case, or like, what is it like working with startups like you mentioned?
Yeah, I mean, it's oftentimes startups are willing to take a risk. So if the big companies, they're not usually worried about cost, but they're worried about timing, market timing. They're worried about failing, and they're worried about doing something that, maybe if it's different. There's the old saying, nobody ever got fired with IBM.
Yeah,
going
that's
with
right.
IBM.
Yeah.
So,
Yeah.
I mean, it doesn't change. I mean, the IBM part changes, but that's sort of nobody wants to get fired. And if you're the kind of person who is corporate, you're there because you don't want to have risk in that part of your life. You don't really, and that's like an absolutely fine life choice. But if you're some person who's like a serial startupper, I mean, you're like kind of a risk junkie.
Yeah, right.
That's absolutely fine too.
Too boring if I just use the off the shelf thing.
Yeah, it's like, because I'm doing this because I want to do my idea the best. I want to be better than everybody. So you're willing to take a risk. I mean, that's the whole point of startups. And so if you have like some technology that's different, but it claims to be better, then startups are often where you're going to get the most interest. Mm-hmm. And working with startups, it's startups have the issue with working with startups is that they usually don't want to be time and materials. Like, if you're working with a larger business, then time and materials is kind of standard, and they expect it, and it's low risk, right? You get paid for the time you put into it. It's nice. It's real nice. But sometimes you got to go and do a fixed price, or a contract that's sort of quasi fixed price, where
right estimated hours with the ceiling, or something like that.
The way that I've usually gone about it is that I'll present a list of deliverables, milestones, if you want to call them milestones, and there will be a payment on milestone of some amount, some prearranged amount. And if you guys decide to part ways, then we don't continue, right? We stop, but at least you get something. And the other thing you can do in these milestone things, it's sort of a trick. It's not a trick, but it's hedging. Is that I would recommend as a strategy to anyone who wants to be a startup consultant, or a consultant who works with startups. There's a bunch of things I would recommend, but one of them that's pretty simple is just to make sure, don't pad your schedule, but there are going to be certain milestones that are going to be really hard, and they're going to take a lot of time. And there are going to be certain milestones that are going to be not hard, and they're not going to take a lot of time. My advice is to kind of normalize the hours on these things. So, that way you can, you're hedging your bets. So if, there might be one milestone where you're effectively getting paid, $50 an hour, and there might be another one where you're effectively getting paid, $200 an hour or whatever.
Right.
But you just want to make sure that at the end of the day, or at the end of the contract, your average billable hours is what it needs to be. Right. So yeah. I think that's the other thing to support. The other little tip is a lot of times, if you can sell hardware, sell dev kits, I don't care, sell anything. You can put cost into that. You can offset your hours by adding cost to the dev kits. A lot of times that's okay. Sometimes it's not. A lot of times people are happier, particularly in sort of like what I would call small businesses, but not startups.
Like SMBs.
They're happier to get something. Yeah, they're happier to get something than to just pay for hours or pay for NRE.
Mm-hmm.
These are just tactics, and as long as everyone's happy at the end of it, you don't have to feel dirty.
Right.
If someone's not happy, then you feel bad, and you're not going to always win. You're never going to always win. It's not every contract's going to be a total victory. You're going to have the occasional disappointed, customer, and it's just going to happen.
Right.
But if you can have happy customers most of the time, then yeah, you're good.
Yeah. What are the different areas that you see people, so specifically like using LoRa type stuff or the Dash 7 stuff and trying to get long range? What are like some of the areas that you see people using this technology in?
It's for Dash 7 over LoRa. It's a lot of mobile stuff, not fixed assets. So if I've got fixed meters, then or fixed anything, if something is fixed in space, I can build my network around it. I can make sure that the quality of service is good enough. I don't have to worry about what's going to happen tomorrow, because the thing's if it's not connecting, it's because of one of a number of issues that are usually not, or I could say they're temporal. Like, okay, a FedEx truck parked in front of the meter, and it's in between me and the meter, and it's going to go away soon. Or something else is like, oh, you got hit by lightning, and you laugh.
Just that little thing, yeah.
But like in lightning prone areas, this can happen. In Florida, like I lived in Florida briefly, like a while ago, but you would see traffic lights occasionally that were just on the ground, and you're, what the heck is going on? And it's because they got hit by lightning.
Okay.
So yeah, I mean, stuff. I'm sure that cellular base stations get hit by lightning all the time down there.
Yeah.
So it's possible, or it could be something like somewhere in between, right? Somewhere in between getting hit by lightning and getting blocked by a FedEx truck. But nonetheless, in the base case, so for most of the time, you can figure out what kind of link budget you need, what kind of sensitivity I need, what kind of power I need to transmit at, what kind of antenna I need to build, how many gateways I need. You can figure all that out beforehand, and you can build your network to meet that requirement. When you start to have stuff that moves around, it gets a lot harder because you can't predict where something's going to be. Is like if I have like animal tracking, like I have a cow, where is my cow going to be tomorrow? If I have if I have a bunch of equipment, like if I'm in a mine and I have all this mining equipment and it's all over the place, I don't know necessarily where something is one day versus the next day.
Right.
Or especially up in Canada, it could snow, and then I've got snow on top of it, and I've got attenuation. So these are the sort of cases where people tend to come to Haystack. They tend to come to us because it's like we have a really challenging environment, and we need all the QoS we can get. So that's in a nutshell. That's it. I don't want to. We have a couple customers at the moment. At this exact moment. I don't want to reveal their exact verticals, but it's suffice to say they're all moving things.
Okay, yeah, that's a good overarching type thing. I was just thinking, like, so when I think about a lot of the LoRa stuff that's out there too, or LoRaWAN, I guess, it is like, it's like sensors in a field, right? It's maybe like agriculture type stuff, or it's a meter, like you said, or just a sensor that's sitting in the middle of nowhere and trying to transmit back. But at a certain point, it's pretty fixed. So that helps.
Yeah, it makes your network deployment much simpler. I can build a good, solid network. I can test it. I can make sure it works. But as soon as stuff starts to move, then everything gets harder.
Yeah. And so you mentioned link budget too. Could you explain what that is?
So link budget is it's a term used by us radio people to describe the amount of energy that is between, let's like the difference of the transmission power and the receive sensitivity, the best case or minimum receive sensitivity of the receiver. So if I take the difference of those two things, I get a link budget. Usually it's expressed in terms of decibels because communication engineers put everything in decibels. That's just what we do. So like a LoRa link budget, if in America I can use, or I should say in ITU region 2, which is North America, and I think certain parts of South America as well. I have a regulatory environment that allows me to use, let's say, in excess of 100 milliwatts if I really want of output power. So 100 milliwatts is 20 dBms, so that's like dB milliwatts. And a LoRa receiver, the book value might say, oh yeah, we can receive it down to about minus 129 dBm, 129 minus 129 decibel,
which is pretty low.
It's not a lot of it. It's like 10 to the minus a lot, right? Milliwatts. It's not a lot of power. It's really impressive that radio works at all.
Right. Yep.
But in reality, what you can observe is about, I think, with a typical LoRaWAN at 1K, I mean, you'll be lucky to get about minus 121, minus 121 decibels. So if I have 20 dBm at the transmit, and I have minus 121 at the receiver, so then I've got 141 decibel link budget. That's pretty good, right? That's not bad. Something like Wi-Fi. I mean, you can pull up a lot of war driving apps. There are quite a few of these. I have one on the Mac called iStumbler, but I'm sure there are dozens of others. And you can see all the different Wi-Fi networks around you, and they usually tell you certain things like they'll give you something called an RSSI, which is just receive signal strength. And that's in a dB. It's going to be a negative number. Like a good strong Wi-Fi signal is going to be better than usually minus 60 dBm.
Yep.
And they'll usually give you some SNR, which is like signal to noise. So, that's just, if you have a lot of Wi-Fi network interference around you, that might go up. Or might go down. Your signal to noise will be worse because you have other Wi-Fi devices in the environment that are interfering with yours, and they're creating noise. So in the 900 band, there is noise, but it's not at all like the case with Wi-Fi. It's much, much less. So you don't have to worry that much about noise in the 900 band. It's not nearly the problem it is at 2.4 gigahertz, and that's good, and especially outdoors.
Yeah, definitely,
especially outdoors.
Well, when you're trying to get like lots of range too, you want to make sure you cover that area.
So so anyway, if I can improve that minus 121 to, let's say, like minus 133. That's 12 dB more of link budget, and in open space, that means, like, due to the way that fall off works. So, like, fall off is kind of quadratic. It's a relationship, and if I have 6 dB more of link budget in open space, I can double the range. So if I have 12 dB more of link budget, I have 4 times the range, and that's,
and just to clarify
the
numbers too, it's because it's going down, right? It's going from minus 21 to minus 133 or whatever you said. That's actually just how sensitive it is, right? That's like saying, if the signal's like that low, I can still get it.
Right. If I add the error correction, I can get some extra sensitivity. That's what that's saying. So if I don't have the error correction, the best I can get, the weakest signal I can receive without errors is maybe minus 121 dBm. And if I add the error correction, the weakest signal I can receive reliably is minus 133. Well, in this particular case.
Got it.
And different error corrections and different modulations it's all going to be different. But in this particular case, I can get a 12 dB gain from from adding error correction. And that's going to result in an enormous improvement of range and quality of service, and particularly just reduced packet loss in sort of fringe areas.
Mm-hmm.
So it's not going to be 4 times in most scenarios. Like in most scenarios where we're going to be deploying any kind of LP WAN or LP LAN, and it's not space, right? It's not we're not shooting this to the moon. So we have other stuff in the way. We have obstructions.
Right.
I have ground bounce, like just the ground. Mm-hmm. The ground is the worst.
Yeah.
The ground is your enemy. If you can put your antennas high, I mean, you can make a huge difference. Even just one antenna high. If you can put one antenna on a roof, or if you can put, on a pole, is even better. But if you can raise an antenna in your system, and that's why all the cellular systems you'll ever see are on poles.
Yep.
That's why they're not on the ground. And just because the ground is such an enemy, the reason for this is something called the Fresnel zone, or I think if you want to be actually correct, it's the Fresnel zone. But I'm not French, so. But that's just that when we see light with our eyes, we tend to think of it being just like a ray, like a point, a line, like a laser or whatever. And we tend to think of line of sight as really like a direct geometric line. But that's just because light is such a small wavelength. Visible light, I mean, a lot of you guys probably know, is between I think like 400 and 660 nanometers. I think that's the wavelength of visible light.
Right.
That's not a lot, right? That's small. It's we're talking terahertz.
Yep.
So if we take this down, if we take this thing down to from terahertz into sub 1 gigahertz, it's definitely not a ray. It's a field. And the field can get impacted by things that you do not think are in the line of sight, the line of visible sight, but are in the way of a lower frequency.
Yeah.
So the ground, like if I have if I have 2 antennas and they're both raised by 2 meters, that's not necessarily line of sight. That's probably going to be non-line of sight. If I go beyond maybe 10 or 20 meters distance, it starts to become non-line of sight at 900 megahertz.
And that's because you're saying the ground kind of cuts off it rounds off the bottom of the transmission path kind of thing.
Yeah, there's sort of this, like, I think people might analogize this as like a football shaped. That's a American football shaped sort of field that goes between the 2 antennas.
Yeah.
And anything that gets in the way of that is going to make it a non-line of sight transmission. So if that's interrupted in some way in the bottom or the top or in the middle, it's going to block. It's going to reduce it's going to cause attenuation is the technical term.
Right.
So we're going to attenuate the signal, and attenuating the signal means less range.
Yeah. Huh. Well, the long distance stuff is definitely interesting to me. I mean, like the fact that you're able to extend it like that. I wanted to also talk about the other thing you've been working on, the Soul Pad. Could you? Mm-hmm. So this is also in the RF domain, but it's you're doing the RF stuff on it, but it's kind of a broader project, right?
Yeah, sort of. That's a good way to put it. I'll explain, I guess. So one of the things that one of the sort of sub-threads of this conversation is about being a contractor or being a consultant. And one of the things that I think you kind of have to be ready for is bouncing in between kind of full-time and consulting and sort of the hybrid of that, like full-time consulting.
Yeah, that's true. Being like on contract for like your entire chunk of time, right?
Yeah, exactly. Yeah. So sometimes, sometimes you're gonna go dry, and you're gonna need to take up work, or sometimes something might just come to you that you really want to do, and it's full time, and maybe it's a little bit different than what you've been doing, and that's the case with SolPad. So SolPad's not a solar company. It sort of seems like a solar company, but it's
it's got soul in the name, so
it's got soul. Yeah. It's a company that builds battery-backed storage and conversion solutions that are, you can use them, I guess, with any DC input, but solar is sort of the predominant input. And this is a startup company, although it's you could call it like a fairly mature startup company, and it's very, very close to launch of the product, and has been on for a while. And it is like, some people lament kind of the death of Silicon Valley. It's just a bunch of media and a bunch of software and a bunch of selling ads to extracting ad revenue.
Right. Privacy problems. Don't forget those.
There are still some hardware companies here. There are still some, and I consider SolPad to be kind of one of those companies that's trying to do something kind of really bold and challenging and different. And I mean, the core idea here is that there's a really sophisticated inverter technology that is being pioneered by SolPad, and it uses a gallium nitride chemistry for the switching electronics, and it's just a new type of semiconductor. It's a new, it's probably been around for 10 years. I don't know.
Yeah, I think so. I'll throw people back to John. Oh man, I forgot his last name now. He was from Cree, and he was here, and he was on the show probably about 6 or 7 years ago now, and he was talking about when they started making gallium nitride switches at Cree.
Yeah, I think it came from blue LEDs originally, but maybe I'm off on that. But you can move a lot of current fast. I mean, you can switch fast. You can move a lot of current without a lot of drive current, and you can switch pretty fast. And so if I can switch fast, it means I can reduce the size of the inductors in my power converter, whether I'm going DC to DC or AC to DC or DC to AC. If I have a faster switching, I can have smaller inductors, and that's really important because inductors are heavy and expensive, and create a lot of magnetic fields, and all that bad stuff. So if I want to have small inductors, I need faster switching, and in addition, if I want to have less heat loss in my transistors, I need somehow more efficient power transistor. And so GaN does these things, and the power team here is done a great job building this really, really efficient, it's called a microinverter, which just means it's small, I guess. That's all it means. It's not micro in terms of power, because it can move, I think, 2 kilowatts, and it's like you can put 2 kilowatts through it, and it's cold. Well, I should say it's not cold, but it's not hot. It doesn't give off a lot of heat, like almost none.
Well, I always think about microinverters too, because you can put them on the back of solar panels, and then you're not combining DC power and making sure everything's kind of matched up. Then you're kind of combining AC power, which allows it works a little bit better usually.
Yeah, that's how this works. So that's the idea behind SolPad, is that it's roof mounted inverters and batteries, which is not something that usually people think of as a good idea. We're going to put batteries on our roof. That sounds like a great idea, right? They're just going to burn my roof off.
Those things that
catch on fire, burn my roof off. So a lot of effort had to be put into validating that the temperatures never get hot enough, and that's been done to validate that you're not going to have a fire risk with this. But part of that is that they have to be light, they have to be small, they have to not crash through the roof, and so forth. So that was the engineering challenge of the inverter, and it's a super impressive piece of technology that I had nothing to do with. Is I guess the short of it. But they all need to be linked up. They all need to be connected all together.
This is sounding familiar now. Here we go.
Yeah. So this is where I came in, and this is where they brought me. they brought me in, and there was actually originally supposed to be a LoRa element to it, but that's been postponed, I think, to maybe V2. But there is still a let's just say it's a non-LoRa IoT data backhaul to get the control signals and get the telemetry of all these inverters, which are usually deployed on a roof. And maybe there are 5 of them. I think they're never more than 25 on a roof, but like let's say a typical is like 5. So that's 10 kilowatts. Standard size of a residential solar deployment.
Yeah.
And so they have to be brought down to a gateway, which is pretty standard concept of operations is to have a gateway, and then the gateway is connected to the internet, so that I don't have all of my embedded electronics, don't have to burden them with IP stacks and all that jazz. So if I can bring that down into a gateway, and I can use some kind of industrial networking in between the gateway and the inverters, then that's what I want to do. That's what
right.
That's the solution that's going to work. And one of the major issue here, like the major challenge, is just having everything be decentralized. And I use the term decentralized. It's not blockchain, right? There's no blockchain happening here.
Okay, good.
But like Dropbox is also decentralized. Git is decentralized, and they're not.
Right. It's just exerting
they're
control without a central master kind of thing.
Yeah, because the last thing you want is to make a 30-year investment in your house and then have the company go out of business. The cloud site goes down, and your investment is bricked.
Right.
Right. So you don't want that.
Mm-hmm.
So this has been an example of something where I've gone and done, and I've learned a lot out of it. This is like that, and I recommend to any person who gets I think the reason why I ended up taking this job is because I'd been doing wireless for so long that I felt like, there are people out there who are put me to shame in terms of wireless and communications technology. And who's that guy? Shiriar on the Signal Path.
Oh yeah.
So he is absolutely legit. He's sort of at the
when
top
you're
of
at Bell
pyramid,
Labs
right?
in charge of the chip design group, that'll do it.
He is absolutely at the top of the pyramid of signal processing and communication, and so that's one direction you can go. And the other direction you can go is to try to broaden your expertise. And so I've tried to broaden my expertise by learning a lot about I guess what falls under the term of SCADA, they call it, which is just industrial stuff linked together in industrial communications. It means something I don't even remember what it means.
Control, and I remember the C is control. I know that for SCADA systems. Yeah,
there's such a huge anybody who's listening and thinking I want to do embedded electronics, and I want to find a way to make cool stuff and sell cool stuff. Look into SCADA, because there's all this old technology, and a lot of it's getting revamped. Just take a look and see if there's any low-hanging fruit there, because certainly, I found it to be sort of a fun challenge to try to modernize a SCADA network for this technology, and I'm sure there are many other opportunities to it. So I'm trying to integrate that into what is generally called the Internet of Things, but what really is just
a bunch of devices talking to each other
on the internet. Getting data on the internet.
Yeah.
Right. So forwarding my field data to a place where I can look at it on a dashboard, or where marketing can look at it on a dashboard.
So you're basically taking each individual panel and then concentrating the data from each panel, and then also you're pushing data back and forth, I guess, as well. And then there's an internet element that basically says collecting all the data and stuff like that, right?
Well, yeah. The real short answer of it is that it's -7 over a wire. So we're using a wire instead of wireless for this, and part of that is just because these things put out a lot of noise.
Oh, interesting. Okay.
And yeah. So, but it's RS-45, and it's half duplex, and it's like RS-45 is kind of like a party line. So in reality, it's a lot like a wireless link.
Yeah,
It's just
right.
wired.
Yeah, you can't have two people talking at once, that kind of thing.
Yeah, exactly.
There's
So
termination in both as well, right?
yes,
An antenna is
just
nothing but a weird terminator.
yes, it's almost the same. So you can find yourself in a place where you can take all the experience that you had and find a different, I guess, vernacular for it, and that's always really fun when you just realize you shortcutted a big learning curve. Is very satisfying.
Yeah,
so
it's like a superpower.
Yeah,
and honestly, for industrial applications too, it's interesting with talking about SCADA systems and stuff. A lot of them are still allergic to wireless just because any amount of packet loss is not really allowed. It's like super controlled. They're like retries. What's a retry? If I retry, the thing friggin' blows up. There you need to have a lot of certainty, and wires usually at least have the view of that, in my experience.
Yeah, I mean that's definitely a marketing. I would say that's marketing first. Wireless stuff now is so sophisticated. Even like off the like if I'm happy to use Wi-Fi, like Wi-Fi is very sophisticated, and honestly, I'll tell you that I think that in many cases their wireless would have been more reliable than RS-45.
Really interesting.
In this, and it's just because there's a lot of areas where RS-45 can go wrong, not because of anything wrong with the wires, but because it's sort of assumed that there's so many solutions for it. There's so many ways to do it wrong, and it's not something that is often really monolithic. It's not like, I just get a RS-45 transceiver and this thing.
Sure. Yeah, it depends who it's coming from and how you're implementing it. What the division thing is, the 1/256 or whatever it is, right?
Well, it's kind of just that every microcontroller that's going to be hooked up to this thing has a different UART driver, and ultimately it hooks up to the UART driver. And like if I have a wireless stack, if I have like a really mature little wireless module, whether it's Wi-Fi or LoRaWAN or Dash7 or whatever, that little piece of technology is responsible for sending my data and getting it right.
Yeah.
And
I guess there's standards bodies there too, right?
Yeah.
I guess that also impacts
it. There's standards, and usually the company has been as nice to make some kind of API for you, even if it's just as simple as AT commands, and that's all been done. And so like a lot of times you'll have problems in an RS-45 or any kind of wire network just because of there's work to do that you maybe didn't realize you had to do to get it to be reliable. And there's more testing because you can't put the testing into somebody else's responsibility. You can't buy necessarily a module that is pre-certified, pre-tested, been used in 1 million deployments or whatever. You can't necessarily do that with RS-45, and so because of that, sometimes there are cases where wireless can be, I won't say more reliable, but easier to integrate in a reliable way.
Yeah. Well, where can people find out more about you and the work that you've been doing?
Well, we blog a lot about it at Haystack. I have a business partner who does a lot of the marketing element of it, and he writes extensively about what we're doing at Haystack. The SolPad stuff you can check out at the SolPad website, which is solpad, solpad.com. And there's a lot of information there. And as far as me personally, I don't really have a rich personal life. My hobby is
working.
Antennas, really. Like my hobby is designing antennas, and that's kind of part of my work as well. So sometimes I like to cook. I have a blog. It doesn't get updated very much. Personal blog. It doesn't get updated very much. That's indegresso.com. And I don't know if there's anything that interesting. There's a big data repository for Dash7 there, but you can check any of that out if you're curious. But if you want to know about Haystack website, haystacktechnologies.com, SolPad website, soulpad.com.
And I wish I would have asked about the antennas earlier. Now, do you write about that too, or is that just for fun in the evenings?
I should write about it more, but
Yeah.
I should. I haven't. I'm going to start. I haven't had a really good way of kind of making it interesting until recently. So, somewhat recently, I started to use MATLAB to simulate antennas, and it might even be possible in Octave, which is open source. I don't know. I know it's possible in MATLAB, and I know that MATLAB has a hobbyist version as well. That's, I mean, I wouldn't say it's cheap, but it's accessible, right? It's not thousands of dollars. I think it's hundreds of dollars. And so that for me is something that I could maybe take and blogging about. Otherwise, you're just like taking photos of messy boards.
This is the shape that I cut out.
Yeah, right. Like I did this because, crazy reasons and, a little bit of math I scrolled on the back of an envelope. But with MATLAB, you get charts and you get, current flow and everything. And you can simulate all that stuff. And it's not like there's higher cost stuff. There's like Ansoft and things that are really expensive.
Right.
Like I think it's like $30,000 for a license for that. But MATLAB ain't bad. Like if I'm not trying to do something ridiculous, if I'm trying to do like let's say I can build a really simple antenna, like just wires, right? I can do that quite easily. That's like a 1 out of 10 in terms of complexity, and then a 10 out of 10 is like something NASA puts on a space probe that they have
it's like baked into an iPhone or something crazy like
that. Like where they have some genetic algorithm running on a supercomputer to like eke out the last 1/100th of a decibel of gain. So
right.
So MATLAB's pretty. I think it can get you to like 7 out of 10. So like that NASA antenna is a 10 out of 10, and like a wire dipole is like a 1 out of 10. And you can kind of get to 7 out of 10 with MATLAB, which is still really awesome. I mean, it's like anything short of like what would go into a cell phone. So like certainly what would go into any of the industrial wireless stuff that I'd build.
That's great. Yeah, I'd love to see that kind of stuff. I'm doing much research around antennas stuff right now as well. So I'm looking for help. I probably will keep you on the line after we stop recording here.
Sure. Well, my 2 cents of advice: if you want to get an antenna done cheaply and quickly,
buy it.
Well, now you can do better than that. Go to. There are many vendors, but I'm just going to recommend one, and that's Johansson. They make a lot of ceramic resonators, and the reason why I tell you to get them is because they make some really simple ones. They make some ones that's basically just like a ceramic core with a coil around it. It's like a helical coil with a ceramic core, and that's going to get you a lot of the way. So I can take that, and maybe it's a 3 gigahertz resonator. Maybe it's an antenna designed for 2.4 gigahertz, and and you have to do something additional to it to get it from 3 gigahertz to 2.4. But let's say I want to build a 900 megahertz antenna. Like often, all you really have to do is run a wire off of it, right? So I just extend. They'll have a little diagram in their data sheet that says for 2.4 gigahertz, add 5 millimeters of wire.
Yeah,
well, what if I add 20 millimeters of wire? What happens then? Like it'll bring the frequency down, and they're easier to tune because that little chip part that you buy is kind of doing a lot of the tuning for you, so you have a lot more flexibility you don't have to get it perfect, and you don't have to simulate it as much. So that's my recommendation for if you're just trying to hack an antenna out and you don't want it to be huge, start with a higher frequency ceramic chip antenna, like for example from Johansson, but maybe there are some others. Extend a wire off of it and see if that works for you. There are some ceramic chip antennas that are more complicated in terms of how they're designed, and they do not work with this this strategy. There's some that are embedded, like PFAs. That's a type of antenna. There's some that are like something called what's called like an integrated magnetic dipole. That's a different type of antenna. Those ones can be really good if you follow the instructions like to the letter on the data sheet, but they're not really good for hacking with. So for hacking, like just the really simple ones from Johansson or Johansson, I think they're called, they're easy to get, they're cheap, and they're easy to hack. So I recommend those.
That's great. That's a great tip. Awesome. Well, JP, thank you so much for being on the show and telling us about Dash 7 and your SoulPad stuff, and now antennas too. It's been a wealth of knowledge, and I appreciate hearing about this stuff.
Yeah, I hope everybody's awake after the end of that.
I'm sure they are. All right, thanks. We'll talk to you soon.
Okay, thank you.